Welcome back to Math 104. Is having asthma independent of being a minor? We decide this by asking, does probability of A given M equal the probability of A just by itself? Does the probability of A after knowing that someone is a minor equal the probability of A before knowing anything about their age? We put question marks here. We need to determine whether this is true. The probability of A given M, that's where we zoom in on the M row and compute 22 out of 251, is approximately equal to 0.0876. This is, however, not equal to the probability of A itself, which is equal to 0.076. The answer, therefore, is no, the events are not independent. Knowing that someone is a minor makes you more inclined to think that the person has asthma. That's because the conditional probability, the after-the-fact probability, is greater than the before-the-fact probability. By the way, we could just as easily have tested whether the probability of M given A is equal to the probability of M. We would reach the same conclusion. Now find the probability that a randomly selected person who doesn't have asthma is an adult. First note that this is a conditional probability. We are randomly selecting from among those who do not have asthma. We are in this column, the A complement column. Zooming in on this column means that we're computing the probability of M complement given A complement. Is an adult, that is not a minor, given doesn't have asthma. This table makes it easy to figure out. There are 695 people out of the 924 we're sampling from who fit the description. So 695 divided by 924, which is approximately 0.7522. The most important thing to understand here is that because of the way the question is phrased, it really is asking for a conditional probability. The background story is we are sampling here from those who don't have asthma, not from the whole population. The two-way frequency table is a very convenient way to represent the given information. But we could also represent that same information in a Venn diagram. This 22 specifically lives in A intersect M. This 229 is precisely the number of outcomes in A complement intersect M. We don't have to do any subtracting off here to avoid overlaps. These already are non-overlapping sets of outcomes. These 54 people live inside the A circle but outside the M circle, while these 695 people live outside of both circles. In this part of the table right here, every entry corresponds to a basic region in the Venn diagram. In a certain clinical trial for a new medical drug, 70% of the patients receive the actual drug, while 30% receive a placebo. So these 30% of all the participants are also taking some kind of a pill, or receiving some kind of injection, or whatever the treatment is, but what the placebo group receives is not a drug at all. Researchers need to set up the experiment with a placebo so that they can tell the difference between the improvement in health resulting from the drug and the improvement in health which would just occur anyway. We're given more information. We are told that 80% of those who receive the real drug get better, while 40% of those who receive the placebo get better. A patient is selected at random. Consider the events A, that the patient receives the actual drug, and B, that the patient gets better. Let's first draw a tree diagram to illustrate this situation. Now this is very important. Some of the given information is unconditional information, and some of it is conditional. The percentages that pertain to all the patients tell us unconditional probabilities. Any percentage, which is a percentage of a smaller group than the whole group of patients, tells us a conditional probability. Conditional upon receiving the real drug, there's a 0.8 chance of getting better. Now the first branching in the tree has to pertain to the entire population, so that must contain the unconditional information. We branch into receives the actual drug and does not receive the actual drug, with probabilities 0.7 and 0.3 respectively. Now from each of these 2 points there will be a branching into gets better versus doesn't get better, gets better versus does not get better. But the probabilities we write on these 2 edges are different from the ones we write on these edges. This number right here is the probability of B given A. This number is a conditional probability, and it is 0.8. If I've gotten to this point in the tree by taking the actual drug, then I have a 0.8 chance of getting better and a 0.2 chance of not getting better. But if I got to this location in the tree, that is, by not receiving the actual drug, then I have a 0.4 probability of getting better, and a 0.6 probability, therefore, of not getting better. These two probabilities have to add up to 1, these two probabilities have to add up to 1, but these probabilities bear no relation to those probabilities. Now let's read carefully. What percentage of patients are recipients of the actual drug who get better? This is a little subtle, but the percentage is the percentage of all the patients. We're asking what percentage of all the patients have the following description. They are recipients of the actual drug who get better. That is to say that they are recipients of the actual drug and they get better. So we're talking here about the probability of A intersect B. The only outcome that contributes to A intersect B was obtained along this particular path. And its probability equals 0.7 times 0.8, which equals 0.56. This is the probability that a randomly selected patient, randomly selected from the entire patient population, does receive the actual drug and does get better. Is this a conditional or an unconditional probability? It is an unconditional probability. It is the probability of an event in which we draw from the entire sample space, not just some subset of it. What percentage of recipients of the actual drug get better? In other words, what is the probability that a randomly selected patient who receives the actual drug gets better? Again, let's read carefully. We are focusing on patients who receive the actual drug. And we're asking, for such a patient, what is the probability of getting better? This is the probability of B given A. This edge is labeled precisely with the probability of B given A. So this equals 0.8, and this is a conditional probability. If this puzzles you what's conditional and what's unconditional, go back and compare the wording of the previous problem to this one. This phrasing limits our focus to those who receive the actual drug, and limiting our focus to them asks, what is the probability of getting better? Before going on to the next video, answer the following question. What is the probability that a randomly selected patient receives the actual drug but does not get better? Is this a conditional or unconditional probability?